At this point, we've seen how to use Maclaurin series to find related functions Maclaurin series. We've seen how to use Maclaurin series to find the sum of certain non-geometric, non-power series. And then we saw a couple of really cool integral problems that we solved using Maclaurin series. For this video, we're going to solve a couple of limit problems using Maclaurin series, and then we have what is possibly the very coolest problem in all of Calc 2. Let's take a look first at question 11. Use a series to evaluate this limit. So the goal here is to look for some portion that we can replace with a Maclaurin series. That's going to be natural log of 1 plus x. We will replace natural log of 1 plus x with its Maclaurin series expansion, simplify. It's going to be kind of similar to what we did back here in examples 3 and 4, the way that we manipulated these fractions. So we'll do a similar sort of simplification for these limits, and we'll get the answer that way. Our limit in example 10 is the limit as x approaches 0 of x minus the natural log of 1 plus x divided by x squared. Whenever we have a limit problem, the first thing to try is to just plug in the value that x approaches as long as it's finite. So if we were to plug in 0 here, we'd have 0 minus natural log of 1 plus 0. Natural log of 1 is 0, so we have 0 minus 0 divided by 0. Well, that's 0 over 0, which is an indeterminate form. So we have 0 over 0, indeterminate form. We could try to use L'Hopital's rule here. That would be one approach. But I'm going to show you how you can use infinite series to solve this without using L'Hopital's rule. Let's take the Maclaurin series for natural log of 1 plus x, and we'll replace this expression with the series expansion for natural log of 1 plus x. From the front of the handout, the Maclaurin series for natural log of 1 plus x is the following. It's the sum, as n goes from 1 to infinity, of negative 1 to the n minus 1 times x to the n divided by n. Let's expand out the first several terms here because that's what we're going to substitute into the limit. So if we expand out the first several terms, we start when n equals 1. When n equals 1, we have negative 1 to the 1 minus 1. We have an even power on the negative 1. So that's going to be a positive first term. X to the first divided by 1, that's just x. Next term, plug in n equals 2. We have negative 1 to an odd power, so we have negative x squared divided by 2. And then plus x cubed divided by 3 minus x to the fourth divided by 4. That should be enough terms to see the pattern. So replace natural log of 1 plus x in the limit with this expansion. X minus the quantity, parentheses are very important here, x minus x squared divided by 2 plus x cubed divided by 3 minus x to the fourth divided by 4, etc., divided by x squared. Notice that x minus x cancels. And I'm going to have to distribute the negative here, so all of these signs are going to actually flip. So I'll have positive, negative, positive, negative. But since the x's cancel, every term in the numerator will have an x squared, which will cancel with the x squared in the denominator. We'll take a couple steps to work through this. We have the limit as x approaches 0. These x's cancel, and then distribute the negative through here, so we're left with positive x squared over 2 minus x cubed over 3 plus x to the fourth over 4 minus etc., infinitely many terms, divided by x squared. We could think of factoring out an x squared from each of these terms in the numerator, or we could just think of canceling out two x's from each term. So we're left with the limit as x approaches 0, x squared divided by x squared, those cancel, so that's just 1/2, minus x cubed over x squared is just x, so x over 3, plus x squared over 4 minus etc. And now we're taking the limit as x approaches 0. There are infinitely many terms here, but each of those terms is going to have some power of x. We'd have, let's see, x cubed divided by 5 minus x to the fourth divided by 6. We're going to have x's in all these terms here. So as x approaches 0, all these terms just go away, and we're left simply with the constant 1/2. That's the answer to this limit. There's one thing that's very important here that is necessary in order to solve the problem. We are taking the limit as x approaches 0. And as x approaches 0, this is important because we are centering natural log of 1 plus x about 0. If we took the limit as x approached, say, 5, we could not use this expansion for natural log of 1 plus x because the Maclaurin series for natural log of 1 plus x will only converge from -1 to +1. So we could only take values here if x approached a number between negative and +1. Well, 0 works. It's within the radius of convergence for this Maclaurin series, so we can replace natural log of 1 plus x with its Maclaurin series expansion, and then after a little bit of algebra, we have the value of the limit. Let's work through example 10 using a similar idea. For example 10, we have the limit involving arctangent. We have the limit as x approaches 0 of arctangent divided by 2x. Once again, it's important that x is approaching 0 here. If x were approaching, say, 5 or 50 or -2, we could not use the Maclaurin series for arctangent. Arctangent has a radius of convergence of 1, so we can only use values where x approaches something between negative and +1. 0 certainly satisfies that, so we can write out the series expansion for arctangent, simplify, and find this limit. We have the limit as x approaches 0, arctangent of x divided by 2x. The key is to write out the Maclaurin series for arctangent. So from the front of the handout, arctangent of x. I'm just going to write out the expanded form of this Maclaurin series rather than the sigma notation, since that's written on the front of the handout. But once again, we want to be very comfortable with going back and forth between the expanded version of the Maclaurin series and their sigma notation form. So arctangent of x is x minus x cubed divided by 3 plus x to the 5th divided by 5 minus x to the 7th divided by 7, etc., etc. In the limit, replace arctangent with that expression. X minus x cubed divided by 3 plus x to the 5th divided by 5. And we're dividing by 2x. We've seen a similar concept where we have a multiple of x cancel in the numerator and denominator. I could think of factoring out an x here, and then the power of x would go down on each of these terms. And then I could cancel the x, numerator and denominator, or I can just think cancel one power of x from each of these fractions in the numerator. We're left with the limit as x approaches 0, 1 minus x squared divided by 3 plus x to the 4th divided by 5 minus x to the 6th divided by 7. The power goes down on each of these fractions because we're canceling an x with the x in the denominator. In the denominator, we're left with a 2. X approaches 0. And even though we have infinitely many terms here, all of these terms after the 1 contain a multiple of x. If x approaches 0, all of these terms just turn into 0, and we're left with 1/2. That's the answer here. This is a limit that we cannot solve directly. If we just tried plugging in 0 to start, we'd have arctangent of 0 over 0. That's 0 over 0. We could use L'Hopital's rule, I suppose. But using Maclaurin series, we can find the limit of this sort of a function. We have arrived at example 12, which is quite possibly the coolest and most beautiful math we'll see in all of Calculus 2. We're going to use the Maclaurin series for e to the x to evaluate e to the I theta. Theta here is just a variable. We can think of it like we think of x. And I is the square root of -1, a complex number. Don't worry, we're not going to get too in-depth with the complex numbers. This is really the only time that we'll have to use complex numbers here. And we're going to see a very bizarre and truly beautiful mathematical result here. Let's take a look. We first need to talk about the square root of -1, which is I. This is the number that when you square it, you get -1. It is not a real number. It is a complex number, or sometimes called an imaginary number. That's not really a great name for it, but it is the complex unit. Let's notice some patterns with I. If we square I, well, this would be the square root of -1 squared. So that's just, well, the square root and the square undo each other, so it's -1. I squared is -1. That's really how we define I. It's the number that when you square it, you get -1. So I squared is -1. What about I cubed? I cubed is I squared times I. I squared is -1, and I is I. So -1 times I is what we have here. I squared -1 times I, or just -I. So I cubed is -I. How about I raised to the 4th power? Well, I raised to the 4th power, we could think of, I'll just write it here. It's I squared squared. And I squared is -1, so -1 squared is just 1. I raised to the 4th power is 1. What about I raised to the fifth? If we do one more power, I raised to the fifth is just I to the fourth times I. So I to the fifth is I to the fourth times I. I to the fourth is 1, so we just have I. We have this cyclic behavior with powers of I. I to the fifth is back to I. If we took I to the sixth power, it's the same as I squared, -1. I to the seventh is I cubed. We have this cyclic nature where every fourth power repeats one of these here. And if this seems a little bit familiar, think of the derivatives of sine or cosine. If you take repeated derivatives of sine or cosine, you start looping back around every fourth derivative. A similar sort of behavior happens here with this square root of -1. Now that we know a little bit about how I works, let's look at the function at hand. We're looking at e to the I theta. And we're going to use the Maclaurin series for e to the x, which is the sum of x to the n divided by n factorial. We are replacing x with I times theta. I is the square root of -1. Theta is just a variable. Think of theta how you normally think of x. If you think of an angle when you see theta, that's good. We're going to see that theta really is an angle in some sense in this problem. So take the Maclaurin series for e to the x, replace x with I times theta. We have the sum, n goes from 0 to infinity, I theta raised to the n divided by n factorial. I'm going to expand out a bunch of terms of this series, and we're going to notice a pattern that emerges. I'm going to do this in 2 colors because this series really is going to split into 2 distinct parts. I'm going to have odd powers and even powers. So n equals 0, I have I theta to the 0 over 0 factorial. When n equals 1, I theta to the first over 1 factorial. When n equals 2, I theta squared over 2 factorial. And we just keep going. I theta cubed over 3 factorial. I theta to the fourth over 4 factorial. Continue the pattern. Now let's group together the same color terms and simplify. I theta to the 0, well, this is just something to the 0 that's 1. So my first term here is 1. And then I'm going to take the second even power term, and I'm squaring I. So instead of writing I theta squared, I can write this as I squared theta squared. And I will replace the I squared with -1. So the I squared becomes -1. My next term is negative theta squared over 2 factorial. Here's my next term. It's going to involve I to the fourth times theta to the fourth. So I to the fourth times theta to the fourth. I to the fourth is just 1. So I can get rid of the I here because I to the fourth is just 1. So my next term is plus theta to the fourth divided by 4 factorial. Next term, I have I to the sixth. I to the sixth loops back around and is equal to I squared. So I to the sixth is -1. So when I take I theta to the 6, I to the 6 is negative. So we just have minus theta to the 6 over 6 factorial. Then finally, I theta to the 8, I to the 8 loops back around to I to the 4th. I raised to the 8 is the same as 1. So I to the 8, that's just 1, times theta to the 8 over 8 factorial. So my next term here, theta to the 8 over 8 factorial. And this continues. Let's take a look at the blue terms now. With the blue terms, the first one is I theta to the first divided by 1 factorial. So I theta to the first divided by 1 factorial. In the next odd powered term, I have I cubed times theta cubed. I cubed is -I. So I'm going to write this as minus I times theta cubed divided by 3 factorial. Next term, I to the 5th over 5 factorial. I'll have an I to the 5th times theta to the 5th. I to the 5th loops back around to just be I. I is the same as I to the 5th. So for the degree 5 term, I have just I times theta to the 5th over 5 factorial, because I to the 5th is just back to I. One more term here, I to the 7th, that loops back around and matches I cubed. I to the 7th is also equal to -I. So I to the 7th here, I'm going to have -I times theta to the 7 over 7 factorial. And this pattern continues. Now look at the terms in red. Does that look familiar? Maybe look at the front of the handout and see if one of the series there expands out like this. This is the expansion for cosine. So all of this infinite series for the first half for all of the odd or for the even power terms, this is just cosine of theta. So we can replace all of these infinitely many even power terms with just cosine of theta, because here we have the Maclaurin series expansion for cosine of theta. How about this portion, the blue terms? Notice that each one of them has an I. You can imagine factoring out that I to have I times all of these terms without an I. So we could factor out an I. If you just think of factoring out an I, then what's left is the series expansion for sine. So all of these blue terms, that's just sine of theta with an I factored out. So plus I times sine of theta. Here we have a truly remarkable relationship. We started with the function e to the I theta. And after doing some Maclaurin series magic, we found that e to the I theta equals cosine of theta plus I sine of theta. This is really remarkable. We have an exponential function here that can be related to trig functions when we bring in the square root of -1, this complex number. Now let's do one more thing and we'll see one of the most beautiful mathematical expressions in the whole world. Let's let theta equal pi. What do we get if we plug in pi for theta? We're thinking of theta as a variable here, and now we see why we use theta, because we're putting angles in here to the trig functions, so it makes sense why we use theta as the variable name here. So take pi and put in pi for theta. E to the I pi equals cosine of pi plus I times sine of pi. Cosine of pi is -1. Sine of pi is 0. So on one side, the I term goes away. This I times sine pi, this just turns into 0 times I. And cosine of pi is -1. So we have e to the I pi equals -1. Or another way to write it, my favorite way to write this expression, e to the I pi plus 1 equals 0. This is an incredibly beautiful statement. We have 5 of the most important mathematical constants in the world. We have 0, the additive identity. We have 1, the multiplicative identity. We have the imaginary unit, square root of -1. We have e, which is super important, and pi, which is very, very super important. This is really crazy. Just by introducing complex numbers, we can get a wild, bizarre, beautiful expression like this. And we know this is true because we use the power of Maclaurin series to prove it. Isn't math amazing? This is so cool.